Probability is a measure of the likelihood of the occurrence of some event. And probability has associated with it quite an elaborate vocabulary. And we're going to talk about that in this little segment. Now, probability, as I mentioned, is a measure of the likelihood of the occurrence of some event. And we're going to actually learn how to assign a number to the probability of the occurrence of the event. But we talk in this environment about an experiment. And an experiment is like rolling a die or tossing a coin. And the outcomes would be the results of the experiment. Now, an event is related to the outcomes because an event is a collection of outcomes. I'll give you an example in just a minute and it'll make this clear. Sample space is a list of all the possible outcomes. Sample space, all the possible outcomes. Now, for rolling a die, the sample space would be 1, 2, 3, 4, 5, 6 because this is a list of all of the possible outcomes of that experiment, you see. And now, in tossing a coin, the sample space would be heads or tails, all of the possible outcomes. Drawing a card, the sample space would be the ace of hearts, the king of hearts, the queen of hearts. You see, there would be 52 items in this sample space if we're talking about drawing a card. Now, let's get back to the notion of rolling a die. The sample space is 1 through 6. The event, we might talk about an event of rolling an even number, you see, and that event would be 2, 4, 6. But there are just those 3 even numbers in the sample space. I could talk about the event of rolling a number larger than 3, and it would be 4, 5, 6. That is the idea for the event notion. Now, we can talk about, and when probability is studied in a more formal setting, hopefully a little more formal than the setting that we're talking about here, we talk about a random variable, which is a function x, which assigns a number to each outcome. And I'll show you an example of how that occurs in just a moment. But we can have a discrete random variable or a continuous random variable. This x value can be discrete or continuous. Discrete means that the number of possible outcomes is finite. You see, finite. And continuous means that the number of possible outcomes is infinite. If you're trying to assign a number, let's say to the heights of all people in a population of some kind, maybe 200 people, how many possibilities are there for the heights of people? You see, when you're doing measurements, it turns out that in almost all of those cases, you're talking about a continuous idea because just between 5 feet and 6 feet, you see, there are an infinite number of numbers between 5 and 6. So we're talking about a variable which could take on an infinite number of different values. So continuous, random, variable, discrete. We're going to stick with the idea of discrete in our study here. Now, frequency refers to the number of times a specific value occurs. Let's look at an example. Suppose 3 coins are tossed, and let's make the sample space of that situation. Now, 3 coins. So on the first coin, we could have a head or a tail. On the second coin, a head or a tail. On the third coin, a head or a tail. So the sample space would have to contain all of the possible outcomes for tossing 3 coins. So it would be head, 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 tail, head, tail, head, tail, tail, and so on, all the way through all of the possibilities. Now, let's set up this discrete random variable idea. Let's let x be the number of heads in each outcome. You see, and how many occurrences of heads do we see up here? Would there be a continuous number of them, an infinite number of them? No, we can see that, gee, heads can occur no times, as in this case. Heads could occur 1 time, as in this case, 2 times, as in this case, and 3 times here, and that's all. So x is a discrete random variable in this circumstance. Now, we can make up a frequency distribution for this situation. For the random variable x can occur, the number of heads can occur 0 times, 1 time, 2 times, 3 times. And x is a random variable, is randomly one of these because the whole idea of tossing coins is a matter of chance. So the number associated with x is random variable. That's how that comes about. Frequency of x, that is the number of associated with each of these values. Well, let's see, for 0, no heads. How many of those have no heads? One of them. How many have one head? If you count through, you get 3. How many have 2 heads? 3 of them. How many have 3 heads? Just one of these. So a frequency distribution. The probability of some event is calculated very simply as the number of favorable outcomes over the number of possible outcomes for that event. And you can find the values here for numerator and denominator by just counting, but a lot of times we need some mathematical formula or some way to generate the number of favorable outcomes and or the number of possible outcomes. Now, the number of possible outcomes is just the number of items that are in the sample space of in our problem. So that's usually pretty easy to count. Another notation associated with this is the probability of x is the number associated with an x over the number associated with the sample space. If we're talking in our previous problem about the probability that x equals 2, now this was the probability that we would have 2 heads. And another notation for it, if we're talking about that exact problem, I could say the probability of heads. You see, and we could go through, and in the sample space, we could actually do some counting to find out how many of the items in the sample space had a 2-head situation. And there were 3 of those, you see. So that's favorable outcomes. And the entire sample space consisted of 8 items. So 3 over 8. 3/8 then is the probability. Now this x equals 2 notation, you see, it's not quite as simple and straightforward as this notation, but this has a more general use, and that's why we put it in here. Now, a probability distribution for the heads and all of that stuff and the number of heads in our previous problems would go like this. X, the number of heads, you see, could be 0, 1, 2, or 3. And the probability of having 0 number of heads, that was the tail situation, there was only 1 of those out of 8. And for 1 head, there were 3 of those out of 8. And for 2 heads, there were 3 out of 8. And for 3 heads, it was only 1 out of 8. Okay, now it's important to know here that the sum of these probabilities, if you add the 1/8, 3/8, 3/8, and 1/8, you get 1. And that's not too surprising when you realize that probability numbers are numbers that are generally between 0 and 1. Now, they could be, a probability number could be 1, could be 0. If an event cannot possibly happen, like if I was going to say, what's the probability that I'm going to win a gold medal at the next Olympics? That probability is 0. There is no chance of that happening. So an impossibility has a probability of 0 associated with it. And something that is assured, like what's the probability that the sun will rise in the east tomorrow morning? Well, that probability is 1. That's an assurity. So probability numbers generally, though, fall between 0 and 1. And the closer to 1 that the probability number is, the more likely the event is to occur. The closer to 0, the less likely it is to occur. Okay, so that's the general idea. Now, expected value of x is a calculation of, let's see, I can describe it as the mean for x values. You know, x values, the mean number of heads that we're going to have in this entire situation, in our whole experiment. What would we expect the number of heads to be? Now, we use x as the random variable here, but you know, x stands for something. It stands for the number of heads that were involved in this 3-coin toss situation. So the expected value of x. Now, I'm showing a kind of a formula here for the calculation, but the calculation is exactly as we have experience with it. Now, just look at this first, and I'll get back to that idea. The expected value of x, all right, I'm kind of making this up. It's the sum of some items that are products here, and I is running from 1 to n, the number of x values that we have, but it's x subscript I, x sub 1, the first x value, times the probability associated with that value. You see, and then we add all of those, and here's the calculation for the expected value of x, or the expected number of heads in our situation. So for 0 heads, the probability is 1/8. For 1 head, the probability was 3/8. For 2 heads, the probability is 3/8. For 3 heads, the probability is 1/8. Multiplying here and then collecting, we find 12/8 or 1.5. So the average number of heads, you see, in all of this business is 1.5. Now, when I say the word average, though, I'm kind of getting in dangerous water here when you talk about formal probability and statistics, because the word average can actually refer to 3 different ideas, mean, median, and mode. And we haven't talked about median and mode, and here we're just now talking about the idea of mean. But the notion of mean, or arithmetic mean more technically, is the notion of average as you are familiar with it. You know, if you want to find the average of all of your test scores, and let's say you've had 5 tests, then you add all of those test scores and then you divide by the number of test scores, 5, and then you have what you call your average. Well, you're figuring out your arithmetic mean for those test scores. And we could take exactly the same view here. You know, we could take all of those number of H's, the number of heads on all of those different combinations that we wrote down. For one, it was 0. For another, there was 1 head. But gee, there were 3 of those, so it would be 1 and 1 and 1. You see, and then for 2 heads, it was 2 and 2 and 2. And then for 3 heads, it was only 1. But you add all those together and you get 12. And you divide by the number of items, oh, that's 8. 12 over 8, 1.5. You see, the calculation is exactly the same as the calculation that we have here. All right. Now, the notion of mean, average, and even median and mode refer to measures of central tendency. How does a group of numbers, how are they clustered near the middle, I guess is a good way to think about it. But it doesn't tell you about the distribution. Now let's talk about several distributions here. Now notice that we have x values here, and we could be talking about this HHH business, but let's kind of get away from that a little bit because I'm talking about 3 different distributions here. So it's not that experiment, but an x of 0, 1, 2, 3, and 4, and the number of items associated with that x is 2, 2, 2, 2. So straight across the board, we have an even distribution here of these values. And in this second, and by the way, the expected value would be, I think, pretty obviously 2 here. And then for distribution 2, notice how the frequencies kind of are nested toward the middle of the distribution. We have a frequency of 4 here and frequencies of 3 right here. But when we perform the calculation for mean, it turns out that it's also 2. You see, so gee, the idea of average on these 2 is exactly the same, and yet the numbers are more frequently distributed toward the middle of the distribution. All right, in distribution number 3, look at how widely dispersed they are. So we have a 5 frequency here and a 5 frequency over here. And yet when we make the calculation for the mean, the expected value, it again turns out to be 2. Now, a notation for expected value, as we saw earlier, is E and then this X business, so it's 2. Another notation that's more often used in statistics is this idea of mu. And so mean is equal to 2. Mu is equal to 2. Now, we're going to talk now about another calculation, a calculation for dispersion. How dispersed is the information, you see, in this distribution? Now, there are 2 numbers that are calculated for this purpose. One is called variance, and the other is called standard deviation. And it turns out that the standard deviation can be calculated from the variance. Now, there are formulas, and I'll show them to you in a minute, but it might be valuable for us to look at these distributions in a graphical form. And in this way, we can kind of see this notion of central tendency versus dispersion. So this one was evenly distributed all throughout the group of x values. The x values are down here, and here is the number or the frequency associated with them. And the x values down here and the frequency associated with them. So we have a kind of a tight grouping here in the middle, and over here we have a wide grouping. So there's greater dispersion here, you see, and there's not as much dispersion here. There's much less here than there is even there. All right, so this is an even distribution. Now, what might we expect? Well, let's just see. Let's go through the calculation and make a calculation for variance and standard deviation on these two. The variance is designated as v of x. All right, and I'm kind of, again, making up sort of a formula here. It's the sum of items as I runs from 1 to n. And notice that it's x minus mu. So it's an x value, it's like the first x, minus mu squared, and then the probability associated with that x. You see, and we add up all those products. You see, but for every one of them, we're taking, this is sort of like distance from the mean. You see, distance from the mean squared times the probability of the occurrence of that x. Distance from the mean times the squared times the probability of that x. And the standard deviation is just the square root of the variance. And notice standard deviation is another Greek letter. This is sigma, and that's the typical or the traditional notation for standard deviation. All right, let's talk about variance for distribution 1. So the variance is, now remember, it's the difference between, it's kind of the distance between x values and standard error or expected value, mean. So it's 0 minus 2. You see the x value minus 2, then squared times 2/10. And then for the next x value 1, minus the mean squared times the probability associated with that. Now for this distribution 1, the mean was, the probability of each one of those items occurring is 2/10, because each one of them had a frequency of 2 and the total was 10. So the expected value of the probability of that occurring is 2 and 10. All right. And away we go with all of them. All 5 or 6 of them, whatever, 5 of them. And then performing the calculations, we find that the variance is 2. Now the standard deviation then is the square root of 2, which is approximately 1.41. Now, let's put that information over here. I just want to kind of put it in the middle. The variance for this one is 2, and the standard deviation is 1.41. Now, we might think about what we would expect for these other distributions. If we understand that variance and standard deviation are measures of the dispersion or the spread of the information, then the information, the data, is not as spread out here, so we would expect a smaller number for the variance and the standard deviation. On the other hand, this information is more widely spread, therefore we would expect a larger number for the variance and the standard deviation, and that turns out to be true. When we go through the calculation on this one, the variance, we would expect it to be smaller now, and it does indeed turn out to be smaller. It's 0.6. And the standard deviation is the square root of 0.6, and it's approximately 0.77. I should put approximations here to be technically correct. And for this third one, we would expect the variance and standard deviation numbers to be larger, and that turns out to be the case. When we make the calculation, the variance turns out to be 4, and the standard deviation is the square root of 4, or 2.